Nice thing about the Gaussian is it's just as likely to be positive as it is negative. So if you add a random Gaussian value to your number, it's not clear which way you're perturbing it. You might be perturbing it up, you might be perturbing it down. Okay? Some other interesting things about the Gaussian distribution. One of them is, imagine that you wanted to pick a random number. Suppose you pick a random number between 0 and 1, and you plot it inside this box. That's not the way to put it. Suppose you pick two random numbers between 0 and 1, and you plot them on the screen. What's it going to look like? It will fill up a box, right? Okay. Suppose you pick two random values from a Gaussian distribution and you plot them. What will it look like? It'll be not lines, these are points. There'll be a few all over the place, but they'll be very well centered. The interesting thing about this is this point cloud will be perfectly round, not squarish. The reason that's interesting is if you pick two values from a Gaussian distribution, they're just as likely to point in any angular direction as any other. Whereas, if you pick from this uniform distribution, even if you center it at 0, do you see that you're not as likely to point in an axis-aligned direction as you are to point towards one of the corners? Because there's more points in here that are in the corner area than there are that are in the side area, because these corners are farther away than the side. So a lot of people think that drawing from the uniform distribution is being totally random. It's actually not. It's biasing you. You're pushing your population in a biased direction. Whereas if you draw from the Gaussian distribution, you're just as likely to push your population this way as that way, and so you're not really biasing it. You're not saying to your population, try to go over that way. You're just letting it wander freely. So the most unbiased, the most free way to perturb your values in your population is with the Gaussian distribution. That's just a gee whiz thing that I think is kind of interesting. That's why we use Gaussian instead of uniform. Make sense? Okay. If you're ever asked to pick a random point on the surface of a sphere, you can do it by drawing random values from a Gaussian distribution and then normalizing them. And it's perfectly distributed on the surface of a sphere. You can't do that with uniform distribution. Okay. One thing with the Gaussian distribution is you have to specify a deviation. Meaning, how far is it this one that's really tall? Or is it this one that's really wide, right? This red one has a deviation of 1. This blue one has a deviation of 0.5. Nope, 0.2. No, that's squared. Square root of 0.2, whatever that is. What's the square root of 0.2?
Irrational.
Yeah, something like that. Okay. And this yellow one has a deviation of the square root of 0.5. Nope, that's this one. Square root of 5. Okay, my point is, if you have a big deviation, it means the points are really all over the place. If you have a small deviation, they're going to be really close to 0, right? What deviation should you use when you're perturbing your values in a genetic algorithm? That's a darn good question, and I don't know the answer. So let's draw a picture, because that always works. Imagine now I don't like that picture. Okay, there's a good picture. I like this one. That looks interesting. Okay, I'm going to use the horizontal axis to represent all 241 weights. Is that how many there were?
291.
291. However many weights there are. Pretend each position on here represents a different set of weights. I only have one axis to work with, sorry, but as I perturb the weights, I'm either going to make my algorithm better or worse, right? I'm going to use the vertical axis to represent stupidity. So what I really want is to get down into this cavern, because this cavern is this cavern of smartness. Here's my members of the population. I initialize them all randomly. Nobody's down in the cavern of smartness. So here we go. These two get together and have a baby. Now they're here. Baby's even dumber than both parents. That's too bad. Suddenly a tournament occurs. Everybody gets in a fight. The worst ones are this one's. That one dies. This one dies. And the baby dies, which is really sad. The mother and father cry. The music plays. Eventually, more randomness happens, and these two get together and have a baby. Ooh, that was fortunate. Now this happens. Baby's down, starting to get into the valley of smartness. You can kind of see how this genetic recombination helps explore the space really quickly, right? Okay. Can't remember when I started talking about that. I wanted to talk about mutation. Now I'm talking about mutation. I'm going to mutate this one. Made it worse. Mutate it again. Yay, made it better. Mutate it, made it worse. Mutate it, yay, made it better. Mutate it some more. Made it better. Mutate it some more. Made it lots better. Mutate it a little bit. Made it way worse. Okay. But the question is, how much do you mutate it by? Right? Well, that depends on the shape of this surface. If the surface is nicely smooth, then kind of doesn't matter. You're just going to roll downhill. In this case, if you mutate it by too much, you see you're just going to jump around. You're never going to get lucky and fall down in here, right? I mean, you might. You never know. You might get lucky and fall down in there, but it's unlikely to happen if the space is really big. Now, this looks hard in one-dimensional space. Imagine now it's 249-dimensional space. This valley could be this, pin-sized divot in this massive space, because you can go in all these different directions. You see how it gets increasingly difficult with dimensionality to get into that hole? So what do you do about that? Well, if your mutation rate's kind of small, everybody's jiggling around and then people are dying, they're going to kind of drift downhill and eventually get down in here. If your step size is too big, you'll overshoot it. But if your step size is too small, it might be that it takes all of eternity to get down in there, right? Can you see that both cases are bad? If your deviation is too close to 0, you'll never get there. If it's close to infinity, you'll never get there. So you have to know the shape of the terrain. The problem is you never know the shape of the terrain. If you did, you wouldn't be using a genetic algorithm. The whole point of a genetic algorithm is this is what you use when nothing else works. And for some reason, genetic algorithms just kind of work in all cases badly. So what can we do? Well, here's a funny idea. Suppose that you've got this chromosome, and what do these numbers represent? Well, in this case, they're the weights of a neural network. But the thing is they could be anything. Anything you want to evolve, you can evolve with a genetic algorithm. That's why genetic algorithms are cool, is they just work with whatever problem you've got. You just throw it in and they work. So what if we use one of these elements to encode the deviation of the Gaussian distribution? You follow me? Essentially what we're saying is we're going to encode the weights of the neural network and some of the metaparameters used by evolution itself. Does that happen in the real world? Do humans contain in their DNA markers that influence how susceptible they are to mutations or to factors that could influence their own genetic recombination and things like that? I claim that, yeah, there are some people that are more virile than others. There are some people that are more susceptible to diseases than others. There's some people that are actually robust to mutations based on radiation and all kinds of things. But whether or not it's biologically inspired, we're going to stick the deviation in the chromosome itself, and then what will tend to happen? Well, the members of the population that have the deviation about right will be the ones that will find their way down here. And the ones that don't find their way down here, they've probably got their deviation wrong, so it's okay if they die. And so over time, what happens is the fit members of the population also have the parameters that are most fit for evolution itself. So essentially, we're going to use evolution to solve the problem of the metaparameters that dictate what causes evolution. Isn't that funky? Okay.
I have a question.
Yeah.
So with this, since there's so many, like 200 and something parameters on it, I don't know the specifics of like how you've done this game, but would it ever be the case that, say for like, whichever of our iterated population is the best, for him, if he's like almost there to improve in some way, like could it ever possibly require like 2 changes to happen together to make him better? Whereas if you just change one, he's bad. If you change the other, he's bad.
Yeah.
But if you do 2 together, he's great.
In fact, absolutely, that is a thing that can happen, and often does. So I guess I'm going to do what professors are supposed to do and throw this back at you. How might one solve that?
Keep a nice one in your population, so over several iterations, those 2 changes have been explored.
Yeah, so there's a lot of ways to do that. Here's the main, well, one way to do it is you could have with some probability not just 1 mutation occur, but 2 mutations occur. Now if you do it that way, then it's going to take longer before you happen to get the 2 right mutations, right? But there's one solution. Another solution is, what if your tournaments aren't the last word on who lives and who dies? So what usually happens in genetic algorithms is when you select the most fit chromosomes to survive, you don't just run a tournament and kill the bad ones. You run a tournament and then you roll dice to see what happens. So maybe with 90% probability the winner survives, with 80% probability second place survives, and with 90% probability the worst guy dies. But there's some possibility that you can actually live even though you're a bad chromosome. And the idea then being, maybe in future generations, the really bad member of the population will find its way into one of these really obscure valleys. For example, this member of the population is looking pretty bad, right? Well, actually it's one of the best, but you could imagine being right next to the big dip and yet still not looking like one of the best members of the population. But if we allow the bad ones to live, sometimes they explore places that we didn't know were awesome and they turn out to be awesome. Okay? Now, here's a question. Would genetic algorithms work if the surface area looked like this? So let's suppose the fitness is just so chaotic that there's no spatial locality of, meaning if you're here, you're no closer to being the best point than you are if you're anywhere else. This is kind of the maze running scenario, right? Would a genetic algorithm work in this case? The part of it that would work well is a really big population. So if you have a humongous population, it might get lucky. But the process of evolving is pretty much worthless. There's no mutation that's necessarily going to make progress, no genetic recombination that's going to make progress. The only thing that's going to help with this type of thing is a massive population. Conversely, what if the topology looked like this? What kind of parameters, meta parameters would be good for this?
Average the parents together.
Yeah, that would do well. I'm going to say that a big population is just going to drag you down in this case, because a big population means everybody's moving at a slower rate. And what we really want is, imagine we only have one member of the population, maybe two, and we just perturb it a little bit. Up, down, up, down, up, down, and we keep keeping the better one. It's basically going to roll down into the optimal spot, and we're going to prevail, right? So when you have a nearly convex error surface, you don't want a big population, you want evolution. When you have a very chaotic error surface, you want a big population, and the evolution's not going to help you very much because it doesn't really occur. Well, where are you going to store the size of your population and the robustness of the population against mutations and the number of mutations and how fast they occur and all these things? A whole bunch of numbers are going to appear in your code, and you're going to realize, oh, I need a number here. Two things you can do. You can hard code it, but what I want you to do is stick those numbers in the genomes themselves and let them evolve, because that's cooler. Okay? Now, sometimes the numbers will become stupid. Like, you can't have a population of -4, right? So you'll have to have a little code in there to check it and normalize it and make sure it's intelligent. But otherwise, that should work just fine. Let's see. I'm hearing a lot of zippers. Am I out of time?
Yeah.
Want to start at 2:30? We start at 2. Okay, I have 1 minute. In my last minute, let's talk about scheduling. Okay, I've talked you through this. There's a couple more things to say about genetic algorithms, but I think you get it. I think you can code it up. I don't think this is a hard assignment. Do you need the weekend?
It'd be nice.
Okay, you got it. I'll give you the weekend. I will make it due Monday. Yeah. Okay, Monday it is. Thanks for coming.